Okay, hi everyone. This is Life Changer Tutorials, and please do well to subscribe. If you are yet to subscribe, just click the subscribe buttons. Thank you. In this very video, we are looking at the relationship between Kp and Kc equilibrium constants. Okay, and here's a simple one. In another video, we saw how this formula is being derived. Okay, Kp is equal to Kc into RT and delta N. Of course, Kp is the equilibrium constant for pressure, Kc equilibrium constant for concentration. R here is gas constant. Now, if the values were SI units, R would be 8.314 joules per mole per Kelvin for SI units. But in this case, we would rather use 0.0821 atm dm cube per mole per Kelvin, because the unit of concentration we use is mole per Kelvin and pressure is the atmosphere. So this value is preferred to be used. Okay. Now, R, okay, T is temperature in Kelvin or absolute temperature. Delta N is the change in number of moles of reactants and products. Remember, we gave something like this, that delta N is equal to C plus D, which is the total number of moles of the reactant, minus A plus B, which is the total number of mole of product minus total number of moles of reactant. Now let's quickly look at an example here. We are given the reaction between nitrogen and hydrogen to form ammonia has Kc 6 times 10 to the power minus 2 at temperature of 500 degrees Celsius. The numerical value of Kp for the reaction is, now in this very question, we are given Kc to be 6 times 10 to the power minus 2. We are also given temperature to be 500 degrees Celsius, which of course we can convert to Kelvin. And adding 273 to convert to Kelvin, that will give us 773 Kelvin. Okay, now coming back to our formula, we have that Kp is equal to Kc into RT delta N. What is our delta N? Our delta N here, we can't tell the value for delta N until we write the balanced equation between nitrogen and hydrogen. And the balance equation is this: nitrogen plus hydrogen giving us ammonia, 2 molecules of ammonia. Okay, and they are all gases. Now the total number of moles of the product, so delta N now is the total number of moles of the product. The product has only 2 moles, so 2 minus the total number of moles of the reactant. Here is 1 mole, here is 3 moles. Remember, you consider only gases and aqueous solution. So altogether 4 moles. So this is minus 4, and that is giving us minus 2. Okay, so substituting the value for Kp here, we can now have that Kp is equal to Kc is 6 times 10 to the power minus 2. Your R is 0.0821. multiplied by T, which is temperature, 773, then raised to power delta N, which is minus 2, like we have here. At this point, we can use our calculator directly here, and we are going to get 1.5 times 10 to the power minus 5. Awesome. So let's look at another question. This example here says if the value for Kc is 13.2 at 30 degrees Celsius, what is the value of Kp for the given reaction? So we are given this reaction. First of all, let's see our delta N. Our delta N, the total for product is 2 minus the total number of moles for the reactant is 2 plus 1, which is 3. Okay, so that's going to give us minus 1. Now my temperature is 30 degrees Celsius. And 30 degrees Celsius, to convert to Kelvin, we add 273, and that is going to give us 303 Kelvin. Okay, so back to our formula. That means our Kp now is equal to Kc, which is 13.2, times 0.0821 times the temperature, which is 303, all raised to power minus 1. And when we do this, we're going to get our Kp to be 0.53. Okay, so we see one more question. It says the equilibrium constant Kp for the following reaction is 1.80 times 10 to the power minus 2 at 698 Kelvin. Calculate the Kc for this reaction at this temperature. Okay, now let's see our delta N. What is our delta N? The total number of moles for product here is 1 plus 1. Okay, minus the total number of moles for the reactant is 2. So we are going to get 2 minus 2, which is actually 0. And we have that our Kp is equal to Kc into RT raised to power delta N. But I want to note something here. In this case, we are given Kp and we're asked to find Kc. So I can make Kc subject of formula. If I want to do that, I'm going to get Kc to be equal to Kp all over RT raised to power delta N, which can also be written as Kp times RT raised to power minus delta N. Now you should take note of that. So if I'm to make Kc subject of formula, this is exactly what I'm going to get. Kp into RT raised to power minus N. That's the difference. Okay, so my value for Kp here is 1.80 times 10 to the power minus 2 into my R is 0.0821 times my temperature is 698 Kelvin, then minus change the number of moles is 0. Okay, so my answer is going to be 1.80 times 10 to the power minus 2. Why? Because the whole of this raised to power 0 is 1, so we are left with this. Thank you very much.